Today's topic is limiting reactant, and we're going to start by thinking about making some s'mores. So if you have 6 graham crackers, 3 marshmallows, and 2 chocolate pieces, how many s'mores are you going to be able to make? With those ingredients, you would only be able to make 2 s'mores. And which ingredient limits the number of s'mores you're able to make? Well, that would be the chocolate. Most of the time in chemistry, we have too much of one reactant and not enough of another. So one reactant will limit how much product we're able to make. And once it runs out, the reaction stops. The limiting reactant or limiting reagent is the reactant that runs out first. It's the one that limits the amount of product we're actually going to be able to make. The excess reactant is going to be the reactant that doesn't run out. So at the end of the reaction, we still have some of that left. It's leftover or it's excess. Now let's apply this to an actual chemical reaction. We have methane or CH4 reacting with oxygen gas or O2 molecules to make carbon dioxide and water. On the left, we have the molecules that are present before the reaction. And on the right-hand side, we can see the molecules that are present once the reaction has stopped. Well, if we look at the molecules after the reaction, we'll see that there are water molecules present and there are carbon dioxide molecules present. And we should expect those because those are the products of this combustion reaction. There's also a methane molecule. That was one of the reactants, and it's still present after the reaction, which means it's excess, it's leftover. We'll notice there are not any O2 molecules. Remember, those would be 2 oxygen molecules bonded to themselves, and none of those are present after the reaction, which tells us that the O2 must be the limiting reactant because it ran out, and at the end of the reaction, it's been completely consumed. You're going to have to be able to determine the limiting reactant conceptually, like we've been doing with the pictures with the s'mores and the molecules. You're also going to be required to calculate the limiting reactant using stoichiometry. And to do that, you're going to set up 2 stoichiometry calculations. First, you're going to calculate how much product is able to be made from your first reactant, and then you're going to set up a new calculation to determine how much product can be made from the second reactant. The reactant that's capable of making the least amount of your product is going to be your limiting reactant, and the reactant that makes the most amount of product is going to be the excess reactant. Let's try an example. 10 moles of aluminum react with 13 moles of chlorine to make aluminum chloride. Which reactant is limiting, which is in excess, and how much product is actually going to be made? All stoichiometry problems can be solved using dimensional analysis, but students who struggle with dimensional analysis oftentimes find they can be very successful with stoichiometry if they use a proportions method. And in this video, that's the method I'm going to use. If you're not familiar with using proportions to solve stoichiometry, be sure to check out my stoichiometry simplified with proportions video. You'll find a link in the description below. We begin by picking one of the reactants. I'm going to start with the aluminum. And I'm going to take the 10.0 moles of aluminum from the question and write it over the aluminum reactant. I need to determine how much product is going to be produced. So over the product, I'm going to write X moles. I'm going to drop my units under the equation. And now I'm going to take the information from the balanced equation. Well, the part of the balanced equation that tells me the number of moles is the coefficient. So underneath the aluminum and the aluminum chloride, I'm going to bring down those coefficients of 2. I have a number above, which is going to become a numerator. The number below is going to become a denominator. And then over on the aluminum chloride, again, I have information above, which would be the numerator. Information below is going to be the denominator. So I'm just going to take that information and write it into a proportion, setting the 2 fractions equal to each other. And to solve, I would cross multiply. And I can see that from the aluminum, I'm going to be able to make 10 moles of product. Well, now I need to calculate how much product can be made from the chlorine. So over the chlorine in the reaction, I'm going to write 13.0 moles. I'm going to drop the unit underneath. And again, it's the coefficient that tells me the number of moles. So I'm going to put that underneath. And now I'm going to have 13.0 over 3 in one side of my proportion. And the other side of the proportion is already set up. I'm still going to have x over 2 moles. So I'm going to set up that proportion, cross multiply to solve. So this tells me that the chlorine that's available is going to produce 8.67 moles of product. So comparing those two answers, 8.67 is the smaller amount, which means the chlorine is the limiting reactant because it made less product. The aluminum can make more product, so it's the excess reactant. And after 8.67 moles of product are made, the reaction will stop. So only 8.67 moles of product will be made in this reaction. Now it's your turn to try one on your own. 80 grams of iron react with 65 grams of water. Calculate which reactant is limiting and what mass of hydrogen gas will be made. So this is a mass stoichiometry problem. You're still going to need to make two calculations, one for each reactant, but in this case you need to incorporate the molar mass into your calculations. So you're going to need a periodic table, calculator, and scrap paper. Pause the video while you work, and when you have an answer, start the video up again. Let's check your work. I'm going to write 80 grams over the iron and x grams over the H2 because we're asked to find the mass of hydrogen gas that will be made. We're going to drop the units underneath and we're going to bring down the coefficients or the number of moles. But since the unit we're working with is not moles, we need to multiply the coefficient by the molar mass. So we would find iron on the periodic table and round its mass to the hundreds place, and that would be 55.85. Going over to the product side, again, we're going to bring down the coefficient. We need to multiply by the molar mass of H2. So the mass of hydrogen rounded to the hundredths place is 1.01, and we're going to multiply it by 2 because there's a subscripted 2 in the formula. So the molar mass of H2 is 2.02 grams. I have numbers above the reaction that are going to become the numerators in my proportion, and I have numbers below the reaction which are going to become the denominators. So when I set up my proportion, I would have 80 grams over 3 times 55.85 grams, and I'm going to set that equal to x grams over 4 times 2.02. To solve for x, we would want to cross multiply, and x comes out to be 3.85 grams of hydrogen. Now I need to determine how much hydrogen will be produced from the water that's available. So over the water in the reaction, I write 65 grams. I'm going to bring down the coefficient and the units. Again, since we're dealing with grams, I need to find the molar mass of the water. So I already know that 2 hydrogens would have a mass of 2.02. I need to add an oxygen to that to find the molar mass of water, and it will be 18.02 grams. That's going to be the left side of my proportion. The right side of my proportion is the same that I wrote in my first proportion because we're working with the same product. So 65 over 4 times 18.02 grams will equal x over 4 times 2.02 grams. Again, we cross multiply to solve for x, and x comes out to be 7.29 grams of hydrogen. And dimensional analysis will give you the same answers as the proportion method that I demonstrated. So looking at our answers, we can see that the iron can make 3.85 grams of product before it runs out, where the water can make 7.29 grams of product before we run out of water. So the one that makes the least amount of product would be the iron at 3.85 grams. So the iron is going to be our limiting reactant. It's going to run out first. The water is going to be left over, so that's going to be our excess. And once we get to 3.85 grams of product, the reaction will stop. So this was a great example to show that even though we started with more iron, the iron is going to run out first. And we only know that if we actually work through the problem and determine how much product each of these reactants is able to make. You did a great job today. Thanks for joining me. I'll see you soon.